Hello and welcome to part two of the talks on the glorious geology of Iceland for everyone. Today we go from Reykjavik to Thingvellir. We imagine we are driving along the Golden Circle. We are starting our real excursion on the Golden Circle. So let's move on. So we imagine that we are driving from Reykjavik to Thingvellir. The Thingvellir fissure swarm, indicated here, is simply the northernmost part of the Hengil volcanic system, which is the red zone here, and perhaps better seen on the next one, this one here. So the Hengil volcanic system is 80 kilometers long, striking or with a direction to the northeast. Hengil central volcano is located here. Then there is the lake. I will show you many photos of the lake. And north of the lake is the Thingvellir fissure swarm, which will be one of the main things we have a look at today. So let's move on. So on the way from Reykjavik here to Thingvellir, this is the lake, we will pass through older rocks. So rocks that initially formed in the volcanic zone here, the Western Volcanic Zone, and moved to the west due to plate movements, due to spreading, as we call it. The numbers you see here are where we would stop if we were driving, and they would show places and views that would be very much worth looking at. Of course, we are not really driving here. We are just imagining we are driving, but I will show you what you would see from the road at these locations here, and then go into the Thingvellir Graben or rift zone itself and discuss what we see there. So let's move on. So again, what we see today and in the coming talks is described in great detail in the glorious Geology of Iceland's Golden Circle and a German translation of that book. So these books are for the general public, and they describe exactly what we see and discuss in these talks, but in greater detail, of course. So let's move on. So what is the first thing we see? Well, we see it already from Reykjavik. It's the large mountain Esja. It's a mountain that rises to over 900 meters above sea level and is around 20 kilometers long. It's a very long mountain. It's composed of lava flows. You see this layering here. These are mostly lava flows, but the brown layers are hyaloclastites, basaltic breccias, mostly formed when eruptions occurred under the glacier during the last ice age or earlier ice ages. And what we see, or ice periods, what we see here are these hyaloclastites. In addition, we see many intrusions and faults. Here is a fault in the lava pile. There's a footpath here, relatively easy to walk up to the top of Esja, which is exceptionally flat, so flat that people have landed aircrafts there, small aircrafts there. And we see big rock slides, landslides, flowing down here. So let's move on. And now we are moving east along the Esja mountain. It is formed through mainly two processes. So the question is, why does Esja stand above the surroundings? Well, there are two reasons mainly for that. One is that the volcanic products piled up in the West Volcanic Zone. So the zone we are going to now, where Thingvellir is located. So the age of the oldest rocks in Esja, which are on the western end of the mountain, is around 2.8 million years. So they are now located 28 kilometers from Thingvellir, So exactly fitting with spreading rate of 1 centimeter per year, that is 1 centimeter per year would yield 10 kilometers in a million years. So the spreading fits perfectly with the age of the mountain. It's simply moving the lava pile, the pile of volcanic processes moving to the west. And the further west we go, the older the rocks, the older the rocks. Here we see dikes, horizontal lavas. They become more inclined with depth in the lava pile, as I'll explain in a moment. We see inclined sheets. These are intrusions, some of them feeding volcanic eruptions. And as I said, we see a dike, vertical, subvertical dikes, and a lot of structures. Asia, in fact, was initially formed primarily from two central or major volcanoes. One is on the western end, and the other one is to the east end of the mountain, and we will look at it later on. So there's one process in the formation of Asia is simply that is piling up of volcanic products in the rift zone and then drifting out of the rift zone through plate tectonic spreading. The other process is erosion. That's primarily the work of the glaciers in the last ice age, so-called Quaternary. And the deepest erosion in this part of Iceland is around 1,200 meters. So the top of Asia at 940 meters is only a few hundred meters, 200 to 300 meters below the original top of the lava pile where it formed. As I said to you, the lavas are mostly close to horizontal, close to the old surface of the rift zone, and then they become more inclined with depth in the lava pile. This is a universal feature in Iceland, and I will explain it in a moment. So the top layers of Asia rose or were uplifted by, say, around 800 meters as they drifted from here, from the active Western Volcanic Zone, or where Thingvellir Graben is located today. Of course, was not when necessarily when Asia was forming, but this is has been drifting to the west through spreading, and part of the uplift is through normal faulting. So there's a gradual uplift. There's a ductile mantle underneath the whole part here, and it becomes, and the lithosphere or the crust becomes thicker when we drift away from the active area, the active rift zone, because of so-called underplating. That means solid material is added at the bottom of the crust, at the bottom of the lithosphere, and at the same time there is glacial erosion moving part of the crust away, and therefore it becomes uplifted. It rises through isostasy, and it rises to an elevation maybe 800 meters above where it used to be here in the rift zone. So this is the way Asia has formed, partly just by piling up of volcanic products, and secondly, or partly by erosion from the glaciers of the Ice Age. Let's move on. So why is the tilting increasing with depth in the lava pile? Well, I explain that now in this illustration. When the eruptive materials pile up, they cause load, pressure on the underlying lava flows. And as they pile up more and more, they press the lavas underneath them further and further down. So the deeper lavas have suffered more in a sense. They have become more inclined, whereas those close to the surface have been less tilted. So that's the way we get gradual increase in tilting or inclination, or what geologists call dip with depth in the lava pile in Iceland. This is a universal feature. We see it everywhere. We see it, of course, in the western part in Asia, but we see it also in East Iceland if we go there. So here again, we are in West Iceland, and we see there close to horizontal the lava flows up here, and inclined by maybe 8 or even 10 degrees further down into in the mountain. So these have been pressed by piling up of new materials in the volcanic zone, in the volcanic rift zone when they were forming. Now we see these are dipping to the east or southeast. They're dipping to the nearest volcanic rift zone, namely to the Thingvellir or the Hengil volcanic system. They're inclined towards west, to east or southeast, towards the present volcanic zone in West Iceland. Then we go to East Iceland, and there we see the same kind of inclination increasing with depth in the lava pile. This is in Hamarsfjörður. That's one of the fjords of eastern Iceland. We are looking north here. So to the left is then to the west or southwest, west or northwest. So here we see that the dip in the top mountains, which rise over 1,000 meters, is around 2 degrees, but 12 degrees in the lowermost part. Again, the erosion here is around 1,500 meters, perhaps slightly more than we see in the Esja area. And the greatest dip here is seen here is 12 degrees. So gradually, the dip or the inclination increases with depth in the lava pile. And the dip in East Iceland is to the west or northwest. In West Iceland, it is to the east or southeast. Namely, always they dip towards the nearest active volcanic zone or volcanic rift zone. When we continue our drive along the Golden Circle, we come to the easternmost part of Asia. This is the easternmost part of Asia. The area here where these cliffs are seen, these gray cliffs, is called Stardown. And it is the remnants of a volcano, the other central volcano in the Esja mountain, the Stardown Volcano. This volcano was active 1.8 million years ago. It was active for several 100,000 years, but its main activity was around 1.8 million years ago. I've sketched here the likely original surface of the Stardown volcano, and then you can see how much has been eroded of it. So the erosion has taken off several 100 meters, obviously. We have these gray cliffs, and we have these pinkish peaks here. And I will speak a little bit more about both of them in a moment now. But this shows what the volcano probably looked like at its peak activity around 1.8 million years ago. So here's a close-up. We see the pinkish peaks. These belong to the Stardown volcano, and this is acid rhyolitic material. These are rhyolitic peaks. There's a big dike, a rhyolitic dike coming from one of these peaks here to the west. And then we see Stardalshnjúka. These are mafic or basaltic in composition, so they're much more primitive, as we say. Strictly speaking, they are what we call microgabbro. So coarse-grained, but not as coarse-grained as you would find in real gabbros. And what are they? They are the remnants of a very shallow magma chamber, This is only a slight or small part of the chamber, only a very small part of the original chamber. And the chamber is located inside a collapse caldera. So the volcano collapsed sometime during its activity and formed a ring-shaped collapse caldera that I will show you in a moment. But the chamber was surprisingly shallow, only at 600 or 700 meters below the surface at the time when it was active. So let's look closer at it. Here we see a close-up of part of the shallow magma chamber with two 2 scales. And you see that these microgabbros, or these mafic intrusion, these are really intrusions, but they acted as a shallow magma chamber. They have a lot of fractures. These fractures are what we call cooling or columnar joints, and they form when the rock is contracting, when it's solidifying and contracting and shrinking, and forms these joints. The most noticeable ones are vertical, but there are also horizontal joints formed as a consequence of this. So it was active for several 100,000 years, the Stardown volcano, and then it collapsed to form a collapse caldera. We mentioned about Reykjavik, that Reykjavik is partly located inside an old collapse caldera from the other central volcano of the Asia mountain. So this volcano, Stardown, also went through a stage of caldera collapse. So what is a caldera collapse? Let's go through that a little bit. A caldera collapse occurs when a ring fracture, I show you only half the ring fracture here. I imagine we cut through the volcano and the caldera, so I show only half of it here. It's a ring fracture. It forms above a shallow magma chamber. So to form a ring fracture, we need a shallow magma chamber. That's a necessary condition, but not sufficient, because the chamber preferably has to be of a certain shape. The ring fracture forms, and the piece of rock, the piston inside the ring fracture, subsides into the shallow magma chamber and normally squeezes out magma. It's not necessarily so that there is any big eruption associated with caldera collapse, but sometimes or often it happens. Now, to form a collapse caldera requires a very special stress field, and that stress field is so that the main stresses, the concentration of the stresses here, must be above the margin of the chamber, and the chamber therefore has to be roughly oblate ellipsoid or coin shaped, like a coin, or we could say, as we call it in geology, a sill-like geometry. So it's very flat. And often of a circular cross-section area in plan view, often of a circular cross-section area and very flat. Then the stresses concentrate above the margin of the chamber, and that can lead to the formation of a ring fault. Sometimes there's a ring dike injected as well, but it doesn't have to be. To indicate how rare it is to form a ring fault, if we look at the 1,500 active on-land central volcanoes in the world, only 4 had a large caldera collapse in the 20th century, and only 2 so far in the 21st century. One was in Reunion as a part of Spain, a part of France, Reunion Island in the Indian Ocean, and the other one was in Kilauea in Hawaii in 2018. So in this century, Reunion was in 2007, and in Kilauea in 2018. They were both collapses of the order of hundreds of meters. Then we had a kind of elastic subsidence in Bárðarbunga in Iceland in 2014-15, but not any major collapse. So this indicates, fortunately, in a way, that something very special is needed to form a major caldera collapse, because I say, fortunately, because very often big caldera collapses squeeze out so much magma from the chamber that we have a large eruption, usually or very often large explosive eruptions. So some of the biggest eruptions on this planet are definitely associated with caldera collapses. So let's move on. When we drive further, closer to Thingvellir, we see a beautiful graben. What is a graben? Graben is subsidence between two parallel fractures, two parallel normal faults. And I indicate here the main faults. Fault 1, cutting through the mountain Botsulur, and fault 2, cutting through the mountain Ármannsfell. In fact, fault 1 is one of the largest normal faults we know in Iceland, with a vertical displacement or subsidence, we could call it, of 400 meters, which is very large by Icelandic standard, very large, 400-meter displacement. So this is a graben, exceptionally clear graben seen in hyaloclastite mountains. So it's formed by cutting through the hyaloclastite mountains, and it is just before we come to the Thingvellir Graben itself. So here is an illustration of a graben. Grabens are normally associated with areas of extension. The crust is moving apart. In Iceland, that extension obviously is related to spreading, plate tectonic spreading. And what happens is two normal faults form, and the strip of land in between, a wedge-shaped strip of land, subsides. And the result is a graben, And because they dip towards each other, the faults, the fractures, therefore it becomes wedge-shaped, and it requires, of course, considerable force to press it further down. And that force is partly, is of course mainly gravity, but that is partly then encouraged or facilitated by of course the spreading, And Thingvellir itself is a graben. Thingvellir is a beautiful graben. Now, we see in Thingvellir Grabens at the surface, and we saw here, the last slide, we saw graben at the surface, but it would be nice to see them in deeper parts of the crust, and we can't do that. Just 10 kilometers to the west of the graben we just saw now, the graben Botsulur and Ármannsfell, is a beautiful small graben exposed in one of the valleys north of Reykjavik in Hvalfjörður, the fjord Hvalfjörður. And here we see a very nice graben, and we see it in a vertical cross-section. So we see what it really looks like, and we can study these faults here and there and compare with what we see at the surface in Thingvellir or in Botsulur and Ármannsfell. So in this case, the graben is small. The displacement, the subsidence is around 30 meters. And you could say, okay, that's very small in comparison with what we have in Botsulur. Yes, it's small, but in fact, it's exactly the same displacement as we see on the main boundary faults in Thingvellir, in the Thingvellir Graben itself, when we go there in a moment. So 30 meters is a significant displacement. It was probably generated in several earthquakes, not a single one, many slips causing this. And as I say, the graben is not very large. It's around 170 meters in width, but it shows in a beautiful section here what grabens look like at the depth of around 900 meters below the surface in a rift zone. So we can compare what we see here to what we see in the active rift zone, 10 to 20 meters to the east, to 10 to 20 kilometers to the east, 10 to 20 kilometers to the east, sorry, and understand the processes, first of all, in 3D, in 3D, and secondly, in 4D, because time comes into this. So we can really understand the processes at depth, the processes we see acting at the surface. We can understand what they look like at depth, what is causing the things we see at the surface. So let's go down further. And now we come to the Thingvellir Graben. This photo is taken, obviously, from the air in the wintertime. It's covered with snow. And we see the whole main Thingvellir Graben here. From this fault here on the western side, we're looking to the northeast. This is the famous hill volcano Skjaldbreiður. Part of the lavas up to here, roughly, they came from Skjaldbreiður, but these lavas here are from a different source. So we see the fault Almannagjá and the fault Hrafnagjá here, and the width of the graben is around 5 kilometers here. There are other faults outside. Heiðargjá is here, so the total width could be around 7 kilometers, but the main graben is around 5 kilometers here between Almannagjá and Hrafnagjá. This, of course, is Lake Thingvellir we see here, and the mountains we've discussed earlier, all covered here in snow. So the lava flows here are 9,000 to 10,000 years old, and I will discuss it later, that in the past 9,000 to 10,000 years, there hasn't been any new eruption. There hasn't been any new eruption there. Why is Thingvellir, which is still quite active, why is it not allowing any dikes to go to the surface? We know there's magma down there, maybe 15, 20 kilometers depth, there's magma there, but it doesn't go to the surface. Now, there are various reasons for that, ways to explain it, but I will discuss some of them now in a moment when we go to discuss a little bit further what could possibly be the reason why we haven't had the eruption in this area here. So just to show it to you, it's the area here. So 4, 5, 6, 7. I'll discuss 8 in the next talk, but I will discuss these areas here now. So we see an outline of the whole area. This is Lake Thingvellir. Here is the Thingvellir volcano. This is the Thingvellir Graben here, north of the lake. And I will show you the fracture, the spectacular fractures here in a moment. What we have been seeing on the way is Esja, which is seen here, Esja up to Stardown. So there were one central volcano here and another central volcano up here on the way. And we saw them, we saw these two western and eastern volcanoes on the way from the road, from stops 1 and 2. And then we saw in stop 3, the beautiful graben of Botnshólmur and Ármannsfell. Then we went down here to this valley here, which extends in from the fjord Hvalfjörður. And here we looked at a beautiful small graben as a comparison with what we see here, and in a way comparison also with what we see here. We saw a graben here at 900 meters depth. So let's now look at Thingvellir itself, and then I will discuss also why there hasn't been any eruption in the area for a long time, for 9,000 to 10,000 years. So this spectacular fault is Almannagjá, the main tectonic fracture. As a normal fault, there has been a subsidence to the left here in the Thingvellir Graben. It marks the western boundary of the Thingvellir Graben. In the distance, we see the Thingvellir central volcano and some of the hot springs and the power plant that is located there, the geothermal fields and the power plant. So Thingvellir is the central volcano to which the Thingvellir fissure swarm belongs. It's a part of the Thingvellir volcanic system. Thingvellir volcanic system. You see here that I will discuss later on the main fracture, Almannagjá, is not just subsidence. This fracture wall is at a higher elevation than here, so there's a subsidence. But in addition, it's very open. There is an opening here in places over 60 meters. So there has been a crustal dilation due to the plate tectonic forces. I will also show you some of the beautiful fracture pattern we see here at the southern end of Almannagjá, where it goes into the lake. So let's move on. So in this illustration I showed you in the first talk, we would say that the Thingvellir volcanic system corresponds to the central one here, not in location, but in mechanics, in the way it functions. Because the central one here has a shallow magma chamber that I indicate, and in addition, the volcanic system has here major boundary faults. So in this illustration, this could be Almannagjá, and this could be Hrafnagjá here. The main faults, and the graben would then be 5 kilometers wide, the main graben. This would be the magma chamber of Thingvellir, and this would be the Thingvellir volcano itself. So this is a very schematic, of course, but it's an indication of how a volcanic system like the Thingvellir volcanic system, how they function. So you have a deep-seated reservoir and then a shallow magma chamber under the main volcano. And I asked earlier, and I pointed out to you that we haven't had eruptions in Thingvellir itself for perhaps 10,000 years, 9 to 10,000 years, somewhere, something like that. Why is that the case? Well, there are several reasons, and one reason is that grabens, while they're active, can for a while suppress feeder dikes. They can either deflect them along the fault, or simply change them into sills. Why? Because when the piece of land, when the wedge subsides, it subsides and presses into the narrower and narrower space here. So there will be, for a while, horizontal compression here. And that leads to dikes going into areas of horizontal compression, changing into sill, into horizontal intrusion. So dike is a vertical intrusion, sill is a horizontal intrusion. Many dikes, they are seen to feed sills in the field. This is, of course, temporarily, because spreading eventually relaxes this effect. And of course, dikes will eventually make it to the surface. We don't know when. Another thing I point out to you here is that many normal faults like this one, they are inclined maybe at 70, 75 degrees at deeper levels, or even down to 60. But when they come to the surface, particularly in stiff lava flows like a Thingvellir, they become vertical. They become totally vertical. That's partly because they originated from vertical tension fractures, later developed into normal faults. So here's an overview, again from the air, showing some of the places I will show you photographs of. This is where most people start, but they come there, they come driving here. This has changed very much. This photo was taken a long time ago. There are plenty of houses here now, and this one has disappeared. So people stop here usually to have an overview of the lake and the graben, and then they walk down here through this entrance down to 5 and 6, and eventually to 7. Beautiful big tension fracture. There's a waterfall here. Uxará is a river here coming down and flowing into the lake. So let's move on. So that's the first view very many people have of Thingvellir. They stop here, there's a fence here today, and they look around the area, and they look along the the main fracture, Almannagjá itself. We see the people here for scale to get an idea of the size of the fracture. This is Axará running, flowing down here from the waterfall above. These are some of the main faults and fractures in the vicinity of Almannagjá. We see there's a tilting here where the people are standing. There's a tilting or inclination of the east fault wall, whereas the west fault wall is totally at the surface, is totally horizontal. This one is inclined. I will explain that later on. So here is the entrance, and we go down the entrance. The entrance is simply the end of one segment of Almannagjá. Almannagjá, like all fractures, is composed of segments of different parts. And here one part is ending, and where it ends, you see the elevation of the fracture walls is the same on either side, meaning there is no vertical displacement, there is no subsidence here. This is pure tension, pure opening fracture, pure tension. The lava flow, which is around 10,000 years old, is composed of numerous flow units. This is typical of Pahoehoe lava flows. Pahoehoe lava flows are usually composed of flow units. Each unit, you see the lady for scale, each unit is around 0.5 meter to maybe 2 meters in thickness, but there are so many that altogether the whole lava flow is maybe several hundred meters thick. But what we see of it here is of course just the part that is exposed due to the displacement on Almannagjá. We see of course cooling joints or columnar joints, I'll discuss more in a moment. The flow of each unit comes from a tunnel, a cave really, a lava tube. And they flow far away from the central crater. Often, not always, but often these are associated with lava shields, like Skjaldbreiður north of Thingvellir. But in this case, the lava flow is not, this one is not from Skjaldbreiður, it's from another source on the eastern side of Thingvellir. So let's move on. Here's a close-up of the flow units. So we see nicely the columnar joints, the cooling joints here. This is a cooling joint, that's a cooling joint, that's a cooling joint. And then we see the contacts between the flow units. So one flow unit is from here to here. Another one is from here to there. And another one starts here, we don't see the top of it. So these are the flow units. They have cooling joints. When do the cooling joints start to form? Well, when the lava comes out, this kind of lava, Pahoehoe, is probably around 1200 degrees. When it has cooled down to around 1000 degrees, it is basically solid. It is basically solid for basalt. It's basically solid. It's not moving anymore. But the joints have not started to form. The joints only start to form when it has cooled further and further down to maybe 700 or 800 degrees Celsius, 800 degrees Celsius, then the cooling joints start to form. Then the column joints start to form. And then as it cools further, the joints propagate into the center of the flow unit. You see also little holes. These are vesicles. These are holes formed when gas was escaping from the cooling lava flow or flow unit. So here's a view to the southwest along the main part of Almannagjá. We see all the way up to the entrance here where we started, all the way up to the entrance. So you get an idea of how big it is. And as I said, the opening displacement from this wall to that wall is in places over 60 meters, So the overall structure of the fault is seen here on the ground, but is probably more appreciated when we go again into the air, as we do in the next slide here. That again is a view from the air of the southern part of Almannagjá, the southern half of it in a way. It's 9 kilometers long, depends on how we define it. It can be regarded as 11 kilometers long, and in a way it continues as faults on the southern part of Lake Thingvellir. But the main Almannagjá itself is the one in this lava flow here, 9 to 10,000 year old lava flow, and there it is around 9 to 10 kilometers long. So here we're seeing the southern part, of the part that most people see when they come to Thingvellir. So that's the entrance that you walk down here, and then you can walk down to the river, to Axará here. Where I've written the word Graben is where it used to be the site of the parliament in the Viking time. They used the cliffs here as to magnify their voices, provide echo, of course, and people gathered here in the Viking time, hundreds, well, in fact, 1100 years ago, 1000 years ago, and later. I will show you here later on what the fracture looks like here and where it enters, more or less enters into the lake. The fractures can be seen in the lake. It continues into the lake, in fact, but I'll show you the southernmost part here in a moment. I'll also show you here an offset. So where this is one segment coming here, ending as a tension fracture, and a new segment takes over. So one segment, this one here, is ending here, and then there is an offset, a shift to the left here, to the east, and a new segment takes over here. And all these fractures are segmented. They're always segmented. That's the way fracture increase their length. It's through segmentation, and the segments then link up to form the longer fractures. The same in volcanic eruptions, in fact. Dike segments link up to form longer fissures at the surface. We see also the inclination here, or what geologists call dip, is 11 degrees, but this one is totally flat at the surface, so this is inclined. I will explain that in a moment. I also draw your attention to the difference between a fault, where one part, this part, has subsided relative to this one. Such faults we call normal faults. But then we have tension fracture, like this one and that one. Tension fracture are just pure opening. They're pure opening. There's no movement up and down or horizontally. It's just pure opening. It's important to distinguish between faults and tension fractures. Faults are related to earthquakes. Tension fractures generate very little earthquakes, and they're always shallow. They never go very deep into the crust, whereas a big fault like this one here, like Almannagjá, as I showed you earlier, presumably goes through the whole crust and all the way down to the magma at maybe 15, 20 kilometers depth under the rift zone. So let's move on. So here are the segments close to the southern end of the main fault of Almannagjá. We see the segmentation here, where they're particularly noticeable where the direction or the strike, the direction of the fault is changing. Then they form this kind of system. I will show you a similar system in a moment. And a new segment comes here. It's offset, and a new segment takes over there. So one straight segment, offset, another straight segment, and then oblique segments that link up to a bigger segment here. So this is the way fractures grow. Fractures on every scale, they grow as segments that link up to become larger fractures. You see the summer houses here for scale. This is, of course, the lake, and you can see fractures here beautifully in the lake. The lake is very, very clear and clean. You can see the fractures here in the lake. These fractures belong to the set of Almannagjá, associated with Almannagjá itself. These are summer houses and cars for scale. So this is very close to the southernmost part of Almannagjá itself, and forms a beautiful set of fractures. The fractures are mostly parallel to each other, so subparallel themselves, but they're oblique to the overall trend or strike or direction of Almannagjá itself. So they're oblique to the overall strike, but themselves form a set of parallel or subparallel fractures. As an indication, the opening here, close to this white car, is around 12 meters to give you a scale, and these are summer houses as well, and of course the car for scale. Such a system of parallel fractures that are oblique to the main trend of the set, or the main orientation or strike of the set, we call anarchelon. And this is a beautiful example of an anarchelon system of fracture in Thingvellir. It's a very, very nice set. So why do we have the friction? Why do we have the tilting? Are these two related? Well, friction occurs on the faults when the fault walls come together. The fault walls come together. And yes, Almannagjá is open at the surface up to over 60 meters in places, but it becomes narrow with depth. And at a few tens of meters, it is closed. And it's still a fault, still a fracture, but the walls are meeting each other. So there is friction. There is friction along the walls. And where this friction really starts, it results in tilting of the eastern fault wall. The eastern fault wall is the one that is moving down. The eastern fault wall is moving down. You could say it's something like that. It's moving down, and the friction causes it to bend here, as we see. So if we say the tilting, if we take the lowermost part here of the ground east of the east fault wall and compare it with the top elevation on the western side of the fault, the overall subsidence or displacement here is around 40 meters. But if we take just from here to here, the maximum displacement is around 30 meters. In fact, maximum I ever measured was 29, but it's around 30 meters here. So therefore, as I said to you earlier, these displacements are very similar to what we saw in the valley close to the fjord Hvalfjord I showed you earlier today. 30 meters displacement. So we can use those as a kind of analogy to what we are looking at here, and understanding what's going on at depth. In that case, depth of 800 meters below the original surface. So that gives us an understanding of the processes, what is going on deeper down in the crust when a fault is moving at the surface, like we see here in Thingvellir today. So here again is an overview. We're looking to the southwest. Almannagjá is of course here. We have discussed that very much. We were looking at the end here now, earlier on. I'm now going to focus on the beautiful tension fractures we see here. They're all filled with very clear and very clean groundwater. Very clear and clean groundwater, but very cold, probably around 4 degrees on average or something like that, 4 or 5 degrees on average. And in this aerial view, we see first a tension fracture here extending into the lake called Silvra. It's very popular for diving. Then we see a small tension fracture here. I will show you in a moment what it looks like on the ground, where there is a tradition for throwing money into it for a long time. People throw money, coins into it. Then comes the next one, Nikulásargjá, but both Peningagjá and Nikulásargjá are simply segments or the southernmost parts of a much bigger fissure or tension fracture called Flósagjá. Now, all these fractures here, and of course Almannagjá, are formed by plate tectonic forces because the country is being, well, ruptured, is spreading due to these plate tectonic forces, in total around 1.8 centimeters per year. But here in this area is much less, around half of it or less than that. So it's spreading like that. And I indicate that spreading in a very schematic way, of course, by these orange arrows. So these are the fractures formed due to plate tectonic forces. They're formed due to plate tectonic forces. So here is Penningagjá, or part of it. The maximum opening is here, from there to there, around 10 meters. Maximum opening is 10 meters. And it is, the open part is tens of meters deep, but the real fracture itself goes deeper into the crust, as I will discuss later on. So it's filled with very clean and clear groundwater, very clean and clear groundwater. It's a pure tension fracture because you see this part and that part, they would fit together. If you move them together, they would fit. There is no movement up and down or sideways. It's not a fault, it's a pure tension fracture. Similarly, the spectacular Flosagjá, where the maximum opening or aperture is around 15 meters. How deep are these fractures? Whether visible, the open depth where you could really go down if you were diving, so to speak, and you could see that the fracture is still open, is perhaps around 25 meters for Flosagjá. The deepest one is probably Silfra, where that kind of depth goes down to 60 meters. The fractures themselves, as a fracture, as a discontinuity in the crust, go deeper. Commonly, they would go down to a few hundred meters. Very rarely much more than that. The maximum, the absolute maximum for a pure tension fracture would be around 1 kilometer. They cannot go deeper than that. Why? Because if they try, they must change into normal faults. Normal faults like Almannagjá. They must, if they try to go deeper, they cannot have the fracture walls at the same elevation. One of the walls will subside. One of the walls will subside, forming a normal fault. So since there is no subsidence here, because we can easily fit the walls together. They're the same elevation. We can easily fit them together. That means that this fracture cannot be deeper than normally would expect, not deeper than several hundred meters, maybe 300 or 400 meters. In an exceptional case, it could go a little bit deeper, but that would be the most likely depth of this fracture. I think it's appropriate to end this talk by an overview of Lake Thingvellir, its beauty, and the main faults, Almannagjá, Hrafnagjá, and this one we didn't really discuss, Heiðargjá here. The main mountains, Botnssúlur and Almarsfell, where we have this Graben here, and Skjaldbreið, the lava shield far in the north, and then Hrafnabjörg we will discuss later in these talks. Then we have on the southern side of Lake Thingvellir, we have the Nesjahraun lava and the islands here into the lake, Sandey and Nesjey. Now the Nesjahraun lava is the youngest lava in the whole Thingvellir volcanic system. And that is still 2,000 years old. So there hasn't been any eruption in the entire Thingvellir volcanic system for 2,000 years, which is quite a long time because this is an active area. All these aspects, particularly, of course, the southern part of the area south of Lake Thingvellir, and particularly the Thingvellir volcano, will be discussed later in these talks. But I think I stop here and say simply thank you very much indeed, and bye-bye.